straightforward, okay? What do you think the numerator degrees of freedom is? 2. And the denominator degrees of freedom is 9, okay? Because the F ratio is 18 divided by 23.3. You just use the corresponding degrees of freedom as your numerator and denominator degrees of freedom. Okay. So then what you would do is we would go to our F table in the back of the book, and then if you don't have your book, it's not a big deal. You can find it. This will be page 629. Okay. Basically, there's like 10 pages of F table. Okay. Each one has a different numerator degrees of freedom. So basically, the first page has numerator degrees of freedom equal to 1. The second page has numerator degrees of freedom equal to 2. So we would go to numerator degrees of freedom equal to 2, and then we would go to the row where denominator degrees of freedom is 9. And then you look up your test statistic. Our test statistic is 0.77. So that tells us that our tail probability is going to be what? Greater than 20%, whatever it is. Okay. That's using the that table. Does that feel okay?
Quick question.
Yes.
Can you explain the numerator and denominator? How did you get that again?
So in my ANOVA table, I have the numerator. I have the between group degrees of freedom as 2, and the within group degrees of freedom as 9. Okay, and so I'm just using those as my numerator and denominator degrees of freedom. My F ratio is the I didn't write this. Okay, my F ratio is equal to my mean squares between divided by my mean squares within. Right? So I just do 18 over 23.33. So the between group is my numerator. So my numerator degrees of freedom is 2. My within group is the denominator, so my denominator degrees of freedom is 9. Alright, so my tail is over 20%. This means I'm using alpha equal to 0.05. Oh, I'm sorry. So my tail area is my p-value. We have a non-directional hypothesis. So my p-value is greater than 20%. My p-value is bigger than alpha, so I would do not reject the null hypothesis. And what that tells us is that I looked at 12 lambs and saw how much weight they gained. And the data that I have is not enough evidence to say that the mean weight gain for any of the groups is different. So, if our null hypothesis, which we might have forgotten from long ago, was mu1 equals mu2 equals mu3, or if we had the tau formulation, it would have been tau1 equals tau2 equals tau3 equals 0. All the taus are equal to 0. And so we would not reject the null hypothesis, and we would say we do not have evidence to say that the mean weight gain from any of the diets is different. I should say is different from the others. if we were to reject the null hypothesis, all we can say is that we have evidence to say that the mean weight gain from at least one of the diets is different from the others. Okay? The weakness to ANOVA is that it doesn't tell you which diet was different. Okay? You don't know which one. So if there was a difference, all you can say is at least one of the diets is different, but you don't know which one is different. And if you want to find out which one is different, then you'd have to go in and do multiple comparisons. So it's kind of a cyclical problem, but at least by doing the ANOVA in the first run, if you come up with no difference, period, then you know at least that part is solved. Okay, let's take a break, 10 minutes.